Chemistry, we're on lesson 5, covalent bonds. We spent the last lesson learning about one of the three major types of bonds, ionic bonds. Now we're going to learn about a second one called covalent bonds. Covalent bonds occur when two or more atoms share electrons. So covalent bonds occur primarily between nonmetals such as carbon, nitrogen, oxygen, phosphorus, hydrogen, sulfur, chlorine, and others. So those are the elements way over on the right side of the periodic table, on the right-hand side. Those are the strong guys, the guys that have high ionization energy and also high electronegativity. They don't give up their electrons easily, and they like to take in electrons from other atoms. Covalent bonds produce combinations of atoms called molecules. Covalent bonds are the bonds that are found in you and other living organisms. So remember, covalent bonds share. They share electrons. So when nonmetals bond, they pull on each other's electrons very hard because both have high electronegativity. Since both have high ionization energies, they don't easily give up their electrons. It's two strong guys having a tug of war. Nobody wins. Consequently, the two atoms share the electrons. So unlike ionic bonds, which is one strong guy, a nonmetal over there on the right, and a metal over on the left, a weak guy, the strong guy totally takes the electron away from the weak guy, and the strong guy becomes negative, an anion, and the weak guy, the metal, becomes positive, a cation. Here you have two strong guys, two nonmetals. They're both very strong. They both want to take the electron away from the other, but they can't. So they have that tug of war, but nobody wins. So as you can see what's going on there, they're sharing the electrons. The octet rule says that atoms are most energetically stable, happy, when they can fill their valence orbital. Octet means 8. It's called octet because elements in the second row, period row, and below need 8 electrons to fill their valence outer orbital. Oxygen has 6 electrons in its valence orbital. To be happy, oxygen would like to fill the 2 empty spaces there. But how is it going to do that? The octet rule says that atoms are most energetically stable, happy, when they can fill their valence orbital. Octet means 8. It's called octet because elements in the second period row and below need 8 electrons to fill their valence outer orbital. Hydrogen's valence orbital can only hold 2 electrons, so hydrogen needs 1 electron to be happy and fill its valence orbital. But how? And note that even though hydrogen's first orbital can only hold 2, not 8 electrons, it's still called the octet rule. The main idea is that an atom wants to fill its valence orbital to be happy. Each hydrogen shares its electron with oxygen. This gives oxygen a total of 8 valence electrons, so oxygen is happy. Oxygen shares an electron to fill the valence orbital of each hydrogen, so the hydrogens are happy. So we'll watch that happen right here. So that hydrogen goes and joins up with the oxygen. The one on the right is going to do the same thing. It comes over and joins up. So now oxygen has 8 electrons in its valence orbital. Originally it had 6, and then it also has the one that's hydrogen is sharing with it on the top, and the one that hydrogen is sharing with it on the right. So it has a full valence orbital, 8 electrons, and so it's happy. Hydrogen originally had 1 electron. It came to oxygen to share electrons, so now oxygen is sharing one of its electrons with the hydrogen, so the hydrogen on the top has 2 electrons in its valence orbital, the first orbital, and the hydrogen on the right has 2 electrons in its valence orbital. Now, one thing you'll notice is that they are double counting those electrons. So those electrons are being shared. So hydrogen believes it owns those 2 electrons. The one on the top believes it owns the 2 electrons up on the top. And the hydrogen on the right believes it owns the 2 electrons in the purple over in the right. Similarly, oxygen believes it owns the 2 electrons up on the top in the purple. And it similarly believes that it owns the 2 electrons on the right in the purple. So effectively, they're double counting them for both atoms. So these are the shared electrons. Because 2 hydrogens fill the valence orbital of oxygen and oxygen fills the valence orbital of 2 hydrogens, this combination creates H2O, or water. These electrons are double counted. They both belong to the hydrogen atom, and at the same time, they both belong to the oxygen atom. Similarly, these electrons over on the right in the purple are double counted. They both belong to the hydrogen atom, and at the same time, they both belong to the oxygen atom. The bonds created between nonmetals by atoms sharing electrons, according to the octet rule, are called covalent bonds. That word covalent, co means together, like to cooperate. It means people work together when they cooperate. So co means together, and valent refers to valence electrons. So the valence electrons are together. They're sharing them. They're working together with them. That's a covalent bond. So remember, covalent bonds share. An elemental diatomic molecule is a bond between 2 atoms of the same element in gas form only. Diatomic molecules are the most common covalent bonds in nature. There are 7 elemental diatomic molecules. 4 of these are halogens with 7 valence electrons. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. One way to remember is that 6 of them form the number 7, and the 7th one is hydrogen. So these are important because whenever you have a chemical reaction that produces, say, hydrogen, it's not going to come out as a hydrogen atom. It's going to come out as a diatomic hydrogen molecule. By the way, let's define that term. It's kind of a long term. Elemental means it's made of just one element. So H2 or N2 or O2. Diatomic, di means 2, so a diatomic means 2 atoms. So it's an element, it's 2 atoms of the same element, and they form, and they're covalently bonded, so they form a molecule. Remember, the halogens are that second to last column on the right. That's fluorine, chlorine, bromine, iodine, right there in the green. Okay? All right, so these elements always form diatomic molecules when they are in gas form. Polar covalent bonds happen when one of the nonmetals is slightly stronger than the other and pulls the electrons a little more towards it. If one of the atoms has a higher electronegativity, it will pull all of the electrons closer to it, creating a polar covalent bond. By polar, what we mean is that one side is a little more negative, that's the side that has the electrons pulled towards it, and the other side that gets the electrons pulled away from it is a little more positive. It's not a full ionic bond, but it's kind of in that direction. One side is a little bit more negative and one side's a little bit more positive. So here in this example, you have 2 nonmetals, but fluorine has a higher electronegativity than nitrogen. So it is going to pull the electrons closer. The electrons will be pulled closer to the fluorine and pulled away from the nitrogen. Fluorine is more electronegative, stronger than nitrogen, which is weaker, and pulls the electrons more towards it. But it does not totally take them away. The atoms still share. They still share the electrons. The stronger atom in the polar covalent bond pulls a little harder than the other, but not hard enough to totally take the electron away from the weaker one. oxygen is more electronegative than hydrogen, so it pulls the electrons toward it. The water molecule below is polar. So let's kind of we're going to kind of section off this water molecule here. The two hydrogens are up on the top, and then the oxygen is down mainly in the blue there. And it has 8 protons, 8 neutrons. So the side of the this side of the molecule contains the nuclei, that's the plural for nucleus, the nucleuses, you could say, the nuclei of 2 hydrogen atoms, 2 protons. The red rectangle has a charge of +2. So if you look at the red rectangle there, it has those 2 protons, but it doesn't have any electrons in it. So it has a charge of +2. This side of the molecule contains 8 protons and 10 electrons. The blue rectangle has a charge of 8 - 10, or 2- charge. So look down there in the blue. If you count the electrons, they're all in the blue, so that's 10 electrons in the blue. And there's 8 protons from the oxygen atom, so that's 2 more electrons than protons, so that's a -2 charge. Now overall, the water molecule is electrically neutral. If you count the total number of protons and the total number of electrons, there's 10 protons, the 8 in oxygen, and 2 in the hydrogens. That's a total of 10. And then there's 10 electrons. You can count them right there. There's 10. So overall, it's electrically neutral, 10 and 10. But the electrons get pulled down toward the oxygen because it's more electronegative. That makes the oxygen side of a water molecule a little bit more negative, and the hydrogen side of the water molecule up on the top in the red a little bit more positive. A polar molecule is an electrically neutral molecule. It doesn't have to be, but in this case it is an electrically neutral molecule that has a positive side and a negative side. This means that it acts like a magnet when other polar molecules are nearby, so it will stick to other polar molecules. Covalent bonds form molecules. These water molecules, for example, are separate structures from all other water molecules. When water boils, the water molecules separate and move freely. So you've all seen water boiling, steam comes up, and that steam is water molecules separating from the liquid water down in the pan, but also separating from each other up in the atmosphere so they can move around separately. So these 2 water molecules can separate and move separately. Think of them much like cars. Two cars can move independently of one another in different directions. Okay, so molecules are separate, independent structures, and we're going to compare that to ionic bonds in just a moment. Ionic bonds form crystal lattice structures. Table salt, that's sodium chloride, has the formula NaCl. There is 1 sodium, that's Na, for each chlorine, that's Cl. The blue Cl, I'm just highlighting that blue Cl atom, is attached to 4 Na atoms. But it doesn't belong to any one of those NAs. It's like bricks in a wall. When you have a brick wall, you don't point to one of the bricks and say it belongs to one of the bricks next to it. It's attached to all of the bricks around it. Same thing here. The chlorine is attached to all 4 of those sodiums. In fact, it would really be 6 sodiums. Because remember, this is a 2-dimensional representation of a 3-dimensional cube of salt. There would actually be a sodium directly in front of the chlorine out towards you, and one back behind the chlorine away from you. But in this representation, we'll just settle for 4. So the chlorine doesn't belong to any one of those 4 sodiums. Similarly, the sodium to the bottom left of that blue chlorine, it's surrounded by 3 chlorines, the blue one and 3 others. So it doesn't belong to any one of those. It's just equally attached to all of them. Again, the best analogy for me is bricks in a wall or apartments in an apartment building. You can tell one from the next, but they're not separate structures like molecules that can move off in different directions. They can't. They're stuck in a cubic structure like that. NaCl is called a formula unit or unit cell because it identifies that there is 1 Na for 1 Cl. In other words, if you take a formula unit, in this case NaCl, and you keep repeating it, NaCl, 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 you'll end up with the crystal lattice structure, the entire cube of salt. A formula unit is not a separate structure in the way a molecule is. You can't pull one of those NaCl units out of that brick wall there. You can't do it. It's stuck in there. So that Cl in blue is attached to all four of those sodium partially, but doesn't belong to any one of them. A formula unit defines the smallest basic unit of a crystal lattice structure, but it is not a separate structure. By repeating the formula unit, the entire crystal structure can be created. So you can see right there, if you take that NaCl in the red box and just keep repeating it over and over and over again, you'll have the entire cubic structure right there. A formula unit is like an apartment in an apartment building. An apartment can be distinguished from other apartments, but it is not a separate structure that can move independently like a car. So that apartment in the yellow box there, you can tell it's separate from the other apartments, but it can't move independently the way a molecule can. It's stuck in the apartment building. Now we're going to talk about Lewis dot structures. These are simplified. What you're looking at right there is a simplified model of an atom. It's what we've learned to diagram using the periodic table how to draw an atom. But there's an even simpler representation, and it actually has some very powerful uses in chemistry that you'll learn later on. So Lewis dot structures are simple diagrams of an atom that only show the atomic symbol and the valence electrons. Remember, it's the valence electrons that become involved in chemical bonds. So they're really the only ones we care about when it comes to forming chemical bonds. So the way you do this is very simple. And this will explain why I had you draw the the electrons around the orbitals the way I did. Start at the bottom, one on the left, one on the top, one on the right, and then when you get to the fifth one, you start pairing them up and going around. You'll see why I had you do that in just a second. So write the atomic symbol for beryllium, so that's Be. And then all you do is the way you see the valence electrons, we don't care about the first orbital or the core electrons here. We only care about those two electrons in the second orbital. We're going to go ahead and place them around beryllium. So draw only the valence electrons around the symbol. So there goes the first one, and there goes the second one, and that's the Lewis dot structure for beryllium. Again, they could have been placed on other sides. You could have placed one of them on the top and one of them on the right. The fact, it doesn't have to be the bottom and the left. That's just the way I tend to draw my atoms and my Lewis dot structures. So Lewis dot structures show only valence electrons, since only these electrons are involved in chemical bonds. Let's do it with an oxygen atom here, okay? How would you do this? Write the atomic symbol O and draw only the valence electrons around the symbol. Again, we don't care about the two electrons in the first orbital. So it looks like this. And that's the Lewis dot structure for oxygen. It's not important which sides those electrons, it's just important that you have two pairs of electrons and two individual electrons. It doesn't matter which side you drew them on. One more, phosphorus. See if you can do this one yourself. Write the atomic symbol, there it is, and place the electrons. Okay, and there it is. So the significance of this layout of the electrons is it says that phosphorus can bond with three other atoms because it has three individual electrons. The pair of electrons on the bottom cannot bond with another atom, but the individual electrons can use a covalent bond and share its electron of phosphorus with three other atoms on three different sides. The water molecule, the oxygen molecule rather, on the previous slide could share with two other atoms, as we saw with hydrogen earlier on. The Lewis dot representation of a water molecule is shown below. So there you go. You have a hydrogen, it has a single valence electron in its first orbital. You have the oxygen, it has 6 valence electrons in its second orbital, and two of those 6 are lone electrons. So they're available to be shared with other atoms. So here we go. All atoms want to fill their valence orbitals. Oxygen agrees to share one of its unpaired electrons with a hydrogen if hydrogen shares its electron with oxygen. So there we go. You see that purple spot, and it's going to come over and share. Oxygen repeats this process with another hydrogen. So there's the lone electron, and the hydrogen comes up and shares. So just like we saw earlier with the full diagram, now we're seeing it with the Lewis dot structure. Both hydrogen atoms and oxygen end up with filled valence orbitals, creating a covalent bond and fulfilling the octet rule. Covalent bonds form molecules. Those are independent structures that can move around independently. They're not stuck in a brick wall or in an apartment building the way ionic formula units are. An elemental diatomic molecule is a bond between 2 atoms of the same element. Elemental diatomic molecules are the most common covalent bonds in nature. There are 7 diatomic molecules. 4 of these are halogens with 7 valence electrons. So one of those is fluorine. So you have an empty space on that fluorine. You have an empty space on that fluorine. So they can come over and share like that. So now both of them have an octet. The 2 in between the fluorines are being shared or being counted by each of the fluorines. So the fluorine on the left has 8 electrons. The fluorine on the right has 8 electrons. Each oxygen atom below has 6 valence electrons for a total of 12, so count them. The valence are only the outside electrons in the second orbital. We don't care about the 2 in the first orbital of each of those atoms. How can we create an octet, 2 octets rather, from 12 electrons? So think about it. Octet means 8. 2 octets is 2 times 8 is 16. But we only have 12 electrons. How can we form 2 octets from 12 electrons? Well, there's a little trick that you can use and that nature uses to do that. It uses something called a double bond. Each oxygen shares both of its unpaired electrons to form what is called a double bond. Notice that each oxygen atom has 8 electrons in its valence orbital because the electrons in the yellow area are counted for both atoms. So the oxygen on the left has 4 valence electrons way over on the left, and then it has the 4 that are in the yellow area. That counts for 8. The oxygen on the right has 4 valence electrons way over on the right, those 2 pairs over there, and it has the 4 electrons in the yellow, so that's 8. So they both have octets. Double bonds are shorter and stronger than single bonds, by the way. The Lewis dot structure diagram for O2 for the O2 molecule looks like this. So in a covalent bond, electrons that bond 2 atoms together are called bonding electrons. Electrons that do not bond 2 atoms are called non-bonding electrons or lone pair electrons. So that's those electrons sitting on the outside that are not forming the bond between the 2 oxygens. A pair of bonding electrons can be represented by a line. Lines should not be used to represent lone pair electrons. So each line represents 2 electrons that are bonding. If you have 2 lines, that represents a double bond. So there's a total of 4 electrons represented by those 2 lines, just exactly what you see up above in the diagram above. Carbon dioxide is what you exhale when you breathe. How does a carbon bond with 2 oxygens? So again, each atom there has to have an octet. And there's 3 atoms. So octet is 8. 3 times 8 is 24. There's a total of 16 valence electrons between the 2 oxygen and the 1 carbon. So you only have 16 valence electrons shown there, but you have to form 3 octets. So how do you do it? So think back to the last example, what happened with the oxygen. So this is what will happen. You can pause if you want to think about it, but this is what will happen. By creating double bonds between the carbon atom and each of the oxygen atoms, octets can be formed around each atom. Notice you have the same number of electrons you started with. You started with 16 valence electrons between the two oxygens and the carbon, and if you count right there, you still have 16 valence or 16 electrons. So you didn't add or subtract any electrons. Carbon forms double bonds with each oxygen. This provided octets for all three atoms. The Lewis dot structure of a carbon dioxide can be drawn with lines to represent a pair of bonding electrons. Carbon dioxide, CO2, has a balanced charge. The two oxygen atoms pull on the electrons equally, so the charge is equally distributed. When electrons are not pulled to one side of the molecule or the other, the molecule is nonpolar. One way you can kind of spot a polar or a nonpolar molecule is nonpolar molecules such as CO2 look balanced. They look even. They look like they're constructed in a balanced way. So you have an oxygen on the left and oxygen on the right. What that means is the oxygens are going to pull on the electrons equally, and so one oxygen is not going to pull the electrons more to its side than the other oxygen because they're equally strong. So you're going to end up with the electrons equally distributed. When you think back to the water molecule, it's kind of lopsided. The hydrogens are over on one side of the oxygen, and so it tends to be polar. When the molecule looks lopsided, it's polar. When it looks symmetrical, when it looks even, then it's probably nonpolar. Now there's a third type of bond, and this actually doesn't have to do with the Lewis dot structure of a molecule. It's a metallic bond. It's the only slide we're going to talk about metallic bonds. So in a metallic bond, electrons are attracted to the protons in the nucleus, but the electrons are not held closely to any particular atom, so they jump from one atom to the next when they are pushed. Copper, abbreviation Cu, has low ionization energy, so it easily passes electrons from one copper atom to another. The yellow Cu circles represent the nucleus of the copper and all the core electrons. And copper has 4 orbitals, so these electrons are coming from the valence orbital to 4th orbital. It has 3 orbitals inside of it. So that's what the Cu in yellow represents, is the nucleus and those 3 core orbitals inside the valence orbital. So the outside, the valence electrons of copper or of most metals are not held very tightly. So they very easily can jump from one copper atom to another. Remember, all the copper atoms are equally strong, so they won't jump over and stay with one the way an ionic bond would. They'll just jump from one to the next, to the next, to the next, and just keep jumping around like that. This is called the electron sea model because the electrons move around like fish in the sea. Okay, so let's review the characteristics of ionic and covalent bonds. We will really not talk very much about metallic bonds at all, so it's mainly ionic and covalent bonds that we'll be focusing in for the rest of this course. So the unit that they construct, an ionic bond, it's called a formula unit, and that eventually forms a crystal lattice structure when you put a lot of formula units together. The covalent bond forms an independent structure called a molecule that can move about independently. It can move around independently of other molecules. It's not stuck in an apartment building like an apartment. Bond formation. Ionic bonds pass electrons. As you learn, the strong guys pull an electron away from the weak guy, so the electron gets passed from one element to the other, from one atom to the other. Covalent bonds, they're 2 strong guys, so they share electrons because neither one can win the tug of war. Elements involved. With ionic bonds, it's a metal, that's a weak guy, and a nonmetal, that's a strong guy. With covalent bonds, it's 2 nonmetals, or 2 or more nonmetals. You can have more than just 2. So that's strong guys, so those are the nonmetals. Physical state. Ionic bonds exist as solids. Covalent bonds can exist as solid, liquid, or gas. So think of water. Water is a covalently bonded molecule. Solid water we call ice. Liquid water we just call water. And gas form of water we call vapor or steam. So covalent bonds, because they are independent, can either stick together or not stick together, and that determines whether they are solid, liquid, or gas. Melting point. Generally, ionic bonds have higher melting points Then covalent bonds. We might do a little experiment with sugar and salt. Sugar and salt look very much the same. You almost can't tell the difference when you just look at them. But salt is an ionic bond, sugar is a covalent bond, and when you heat them both up, you'll find that the sugar will melt, but the salt will not. Solubility in water means how much do they dissolve. Ionic bonds dissolve in water. Salt dissolves very easily in water. Covalent bonds don't. Now, when you put sugar in a drink and you stir it, you may think, well, it's dissolving. But it's not. You're not breaking up the sugar molecules. You're simply getting one sugar molecule to separate from other sugar molecules. So in that sense, it's not dissolving. Whereas with an ionic compound such as NaCl, you're getting the Na plus ions and the Cl minus anions to break apart in the water solution. So you're really dissolving the compound. Covalent bond, you're just separating the molecules, but the molecules stay together. Finally, conductivity, that has to do with how much they conduct electricity, and ionic compounds are very good conductors. They're called electrolytes, and covalent bonds such as sugar are very poor conductors of electricity. So that takes care of this lesson on covalent bonds. And a little bit on metallic bonds too. So we've covered all three types of the bonds, and those are the only three ways that atoms in the universe connect with one another to form new compounds. Those three ways that we've learned in the last few days. Okay, so now we're going to get into some chemical reactions and chemical formulas, and that's when we really get to get in the lab and make some chemistry happen as you learn to do that. Okay, great. So we'll see you on the next lesson.